triad of chymotrypsin gives a really good example of how we can go through in explaining enzyme reaction mechanisms and the types of catalysis that we use. That's why we talk about chymotrypsin so much. Not just the fact that it's a useful enzyme, but the fact that it uses so many different forms of catalysis, or of formats of catalysis: acid, base, covalent, all that stuff. So for the catalytic triad, in the center of it we have asparagine. In the center of it we have histidine. I'm just going to abbreviate that as HIS. So here's how I'm going to draw this. Here's the active side of it. We have these three compounds, these three molecules kind of jumping out at the steeple part of our active site. Remember the analogy of it being that there's mostly the unreactive hydrophobic stuff is at the base and the reactive stuff is more at the tip part of the steeple. So if you remember back to this class, or to even organic chemistry earlier, histidine really isn't going to be, this nitrogen atom here is not going to be protonated until it's under pretty acidic conditions. But what it does have is in this nitrogen atom here, because of the heterocycle rule, those lone pairs in that nitrogen are going to be far more reactive than that of these. And so they're going to pull on anything that they can kind of get their hands on in close proximity. So what's in closer proximity to histidine, and just in case you know that histidine is located at position 57, I didn't mention that, but I didn't really feel like it was superbly necessary. But right next to him, or not right next to him in terms of sequence, but right next to him in terms of the three-dimensional active site that we have here, is serine. This is a position in the sequence of 195. For purposes of this, I'm not going to draw the actual structure of the heteroatoms, but if we were to look at this right here, this nitrogen here is going to kind of pull ever so gently on the hydrogen. Kind of imagine him pulling on this hydrogen of the oxygen, kind of stretching that oxygen out, kind of holding him down, ready to just kind of beat him up. And eventually he's going to deprotonate him, but I'll talk about that later. So there's histidine, serine, and the other part of the catalytic triad, aspartic acid, or aspartate in this context, because it's obviously under physiological pHs, it's going to be deprotonated. So I'm just going to go ahead and draw it in one resonance structure. I'm not going to necessarily draw it as a hybrid, but just like we had over here, a negative end or a group of electrons pulling down on the hydrogen of this one, we have this guy here. He's going to be pulling that hydrogen towards there, and I'll go ahead and use an arrow to indicate that this is being pulled in this direction here. So I guess if we were to write down here the functions of each of these, so for that of the serine, this is an arrow here. I'm not drawing it saying that that's connected there. Maybe it's really there. That's our enzyme, three-dimensional structure. How scientifically fancy of me. So for serine, at least, the purpose of this is it's going to be deprotonated by histidine. So if you think back to the types of catalysis that we have, there's one of them where anything other than water is acting as an acid or a base. This deprotonation is going to give us the alkoxide anion, which, if you remember from general organic chemistry, this is a nucleophile, and this nucleophile is going to undergo a nucleophilic attack at the carbonyl of the peptide bond. I don't think you really need to know the structure so much. I mean, it's interesting, but the catalytic triad is just a good example of how all the different types of covalent factors can come into play, and the action of chymotrypsin is a good example of catalyses of all types. So for histidine, he's going to pull on the hydroxyl group of serine. This is undergoing a basic catalysis. It's going to pull on the gold OH of your serine, and then last thing that we have is aspartic acid, which in this context is aspartate. It's being deprotonated. This is going to go ahead and make sure that histidine is in the right orientation. So if this was a majors course, we probably would learn the reaction mechanism for that of chymotrypsin, but we're not going to. But we do need to know this because this is an example of covalent catalysis, acid-base catalysis, and then for here, approximation and orientation catalysis. So I'm just going to say approx / orientation Catalysis. My handwriting is bad. And then this would be covalent catalysis. Covalent catalysis. Cool.